Hey guys, hello everyone and welcome to the channel. So today in this particular video we are going to take 5 simple questions which can be asked from your quantum chemistry and which everyone can solve, right? That means you don't need much of your mathematical knowledge to solve these questions. Like, these are pretty simple questions which any one of you can approach. If you are one of them who don't like quantum chemistry or who fear quantum chemistry, then this video is for you, right? So I'll be taking these 5. There are many questions actually, but I have just taken 5 types of them which I personally feel they are very simple and which every one of you should approach for, and they generally come in the exam as well. So that's why I have taken, and that's why I made this video, because for the upcoming exam this is going to be highly important, right? Now before starting this video, I want to inform you that I teach on Unacademy platform and my courses regarding the revision of your CSIR NET exam is already running over there. I cover all of the syllabus for the CSIR NET exam. So if you are interested in joining Unacademy Plus and if you want to take classes of mine live over there, so all the information regarding the class has been given in the description of this video. So having said that, let's continue with our video. So before starting anything about quantum chemistry, it's very important to have basic understanding or the basic information about the operators. So here's a list of all the common operators which you need to know, like your position operator, your linear momentum operator, kinetic energy operator, angular momentum operator, and your Hamiltonian operator. So these operators which I have mentioned on this particular slides are all in one dimension. Okay, that means all of them are in x dimension. All of them has been taken in the x direction. If you change them, like if you want to make the operator in the y direction, then the x will be changed with the y, okay, and so on and so forth. If you want to find out the operator in the 3 dimension, you just have to add the operators, the corresponding operators in x, y and z axis all together. That's how it will be done. Now once you are done with the basic operators, now we can go for the types of questions. So the first type of question which I have taken is pretty simple and pretty obvious, that is eigenvalue and eigenfunction type of question. In these types of question, you will be given with a operator, and you will be given with a wave function, and you have to operate that operator on the wave function so that you get the wave function back. Okay, now along with that wave function, whatever constant you get, that constant is called as the eigenvalue. I hope most of you know about it. If you don't know about it, and if you want to if you want to learn more about this particular concept, then I would suggest you to watch my video on eigenvalue and on the operator. So there I have discussed all these eigenvalue and eigenfunctions. So you'll be able to cover this particular topic from there, right? So this is the first type of question. Now what you I have just given an example over here. Like, it will be given that check whether this psi is a wave function which is e to the power 5x is a eigenfunction of the operator. The operator is given to us as d by dx. Now what you have to do, you have to operate this operator on this wave function. So a psi, that's what I'm going to do. I'm going to operate a as my operator on the wave function psi. So when I will operate that, you should know this thing, that d by dx of e to the power ax, if I have ax, that means if I have coefficient of x as a, so I'll be getting a e to the power ax. Okay, so e to the power ax will remain as it is, the coefficient of x will come as the product over here. So the same thing is here. We are having 5x, so we can write down it as 5 times of e to the power 5x. Now e to the power 5x was what? That was equals to your psi, so I can write down psi over here. So what I got a psi. I just operated a on the psi and I got my psi back along with a constant, and that constant is that constant is 5. So my eigenvalue is 5 and psi is my eigenfunction. So this is how you have to do. Although in the exams there might be different questions based upon it, so I would recommend to you to solve previous year's questions based upon eigenvalue and eigenfunction, right? So this is the first type of question. Now for your practice, I would highly recommend you to solve this particular question. This was asked in your GATE 2013 exam, and it says that e to the power minus 2 x square is a eigenfunction of the operator. So this is the operator given. So you can consider this particular whole thing as an operator, and you can consider this as my psi, as a wave function. Now it is asked that what is the eigenvalue. So same thing you have to do. You have to operate this operator on the wave function, and you have to do it in a such a way and you have to see that at the end you are getting your wave function back. Whatever will be left out with the wave function will be your eigenvalue. So I just want you guys to practice this. That's why I'm giving this question for you. You have to tell me in the comments, in the comment section of this particular video, that what answer you got for this. All right, so let's see what answer did you got. Okay, let's go to the next type of question now. The next type of question is to find out normalization constant. Okay, now these types of questions are asked when a particular wave function will be given to you, and it will be asked that what is the normalization constant for that. So a wave function basically is said to be normalized if it follows this particular condition. That means, so if you multiply the wave function with the complex conjugate of it, and if you integrate that over the given interval, that is going to give you 1. Okay, and if it gives you 1, then only the wave function is said to be normalized. This is in the like in the usual representation, and this is the Dirac notation in which you can represent the same normalization condition. Okay, normalization constant is given by n, and that can be calculated using this particular equation. So normalization constant n is given by this particular equation. It says n is equals to 1 upon and this particular whole thing. Okay, so whenever a wave function is given to you, and if you want to find out the normalization constant corresponding to that, so you have to put it over here to solve that. Okay, so I would recommend you to solve certain questions related to this normalization constant as well. Let's go for the next type of question. The next type of question is pretty simple, which I feel is the easiest one, and where you are given with a particular energy level, and like it can be given about the particle in a 3-dimensional box. It can be also asked for the particle in 2-dimensional box, or for the particle in a 2-dimensional square box, or in a 2-dimensional rectangular box. So you have to practice those questions as well, but the basic thing which you need to know is particle in a 3-dimensional cubic box is going to have energy in this formula, that is nx square plus ny square plus nz square h square upon 8 ml square, and the combination of this nx, ny and nz is going to give you the degeneracy. Different combinations, the number of combination is going to give you the degeneracy of the system. So for example, if I have the question in such way that the energy is given to me as 14h square upon 8 ml square, if it is given in such way, so I have to find out the values of nx, ny and z, so that I can get 14 out of that. Okay, now you know that if I keep my nx is equals to 3, ny is equal, so if I keep my nx is equals to 3, so 3 square plus 2 square is already going to give me like 9 plus 4, it's going to give me 13 plus 1 square. So that's what I can have, right? 3 square plus 2 square plus 1 square is going to give me 14, because 3 square is 9, 2 square is 4, so 9 plus 4 is 13, plus 1 is going to give me 14. So nx, ny and z can have values like 3, 2 and 1. So I have to find out the combinations now. So the combinations will be done like this. So I can either combine them in this order, that 3, 2, 1, I can either write them like that, or this is the one of the combination, or I can write down 3, 1, 2, this is the second combination. The third one goes like 1, 2, 3, or 1, 3, 2. Okay, then I can have like 2, 1, 3, or I can have 2, 3, 1. So how many combination did I got? So 1. So I got combination 1, 2, 3, 4, 5 and 6. So 6 combination. So the degeneracy of this particular energy level will go as 6. Okay, so it's as simple as that. So you can solve any question which is asked from the degeneracy regarding like of a particular particle in box like that. So I have made a particular separate video on this particle in a box problem and the degeneracy related to that, and all the questions related to that have been discussed in that video. So I would highly recommend you to watch that video as well. Okay, so the link of the video is there in the I button. You can click over there and you can watch that particular video. So it will be very helpful for you for your quick revision of the topic. Alright, let's talk about the next type of question, which is actually the part of your degeneracy only, but now the particle will be in your 3-dimensional simple harmonic oscillator. Okay, so the energy goes like nx plus ny plus nz plus 3 by 2 h cross omega. Okay, so this is what is the energy for a particle in 3-dimensional simple harmonic oscillator, and the degeneracy is again the combination of your nx, ny and nz. So in the same way as we did earlier, you have to do here. The thing which you have to see is that the square is not over here now. Okay, so you have nx plus ny plus nz plus 3 by 2 h cross omega. So you can just find out the different combinations of them to find out the degeneracy, but the system is different. Here the system is in 3-dimensional simple harmonic oscillator, here the system is 3-dimensional cubic box. Okay, the next type of question, the fourth type of question which I find easiest one is from the Huckel molecular orbital related question, okay, where there are three types basically: finding HOMO, finding LUMO, or finding the highest energy orbital. So let's see how to do these types of question. They are pretty simple to do. Let's say I have taken example of butadiene. So a butadiene, in the question they will be asked ki what is the HOMO, or which of the following is the HOMO for a butadiene molecule. So a butadiene orbitals, the molecular orbital of the butadiene will be drawn like this. Okay, you all know how to draw the molecular orbitals of butadiene. So this is how it will be drawn, looking upon the number of nodes. So the number of nodes, okay, number of nodes basically is equals to n minus 1, where n is the energy level which we are talking about. So for first energy level, 1 minus 1 will be 0. So there will be no node here. For the second energy level, it will be like 2 minus 1. So one node will be here at this particular point. At this point we will be having a node. So a node is the point where there is 0 probability of finding the electron. Okay, for size equals to 3 or energy level 3, we will be having 2 nodes. Those nodes will be at these 2 positions. For size equals to 4, you will be having 3 nodes. So they will be given at these 3 positions. Okay, so that's how it will be. Now you have to identify, they will not give you in this way, or they might give you in this way, but you have to see, you have to be able to find it out through the wave functions given. So the wave functions are given to you in the question as a option. So there you have to see that how many times the sign is changing. So here the sign is not changing at all, that means there is 0 node. Here the sign is changing just once. See, the sign has changed just once over here. Okay, just at this particular point, like from here to here. So one node. Here you can see the sign has changed here from plus to minus, and then again from here to here, from minus to plus. So 2 nodes in this case. And for this one, the sign has changed once, then twice, and then thrice. So the sign has changed 3 times. So 3 nodes are there. So just looking upon that how many times the sign has changed, you can find out the number of nodes in that particular orbital, and with that you can find out that which energy orbital it belongs to. And if you found that, you can tell that whether it is HOMO, LUMO, or what. Because in butadiene, if it is not in excited state, if it's just in a ground state butadiene molecule, so you know that this will be called as your HOMO. Okay, the psi 2 will be your HOMO, and your LUMO will be your psi 3. Okay, that's how it will be done. So this is pretty simple. The things become little tricky when you have allylic system. Now allylic system can be allylic radical, allylic carbocation, or allylic carbon ion. So if it is allylic carbocation, so carbocation will be having like 2 electrons. So this is how the electrons will be filled. So the HOMO will be this. For allylic carbon ion, you will be having 4 electrons. So the electrons will be filled up till here. Okay, so this is for carbon ion. Okay, and this is for carbocation. Okay, and the last one which we can have is for your radical. So for the radical, you will be having 3 electrons like this. Okay, this is for your allylic radical. So that's how it will be. Now again the same thing, you have to identify the HOMO, LUMO, or they might also ask you to find out the highest energy orbital. So the highest energy orbital is this. This is the highest energy orbital, psi 3. So you can just again same way you will be able to do, that is just by finding out the number of nodes. One thing which you have to focus on is that in the case of psi 2, your like the second orbital or the second lobe is missing, because the node is actually lying on that particular point. So that's why in the formula or in the equation also your phi 2 is missing, because there is no phi 2 over here, because the electron density at phi 2 is 0. So that's why that is not there in the linear combination equation. Okay, so Huckel molecular orbital has to be studied in detail, but if you have not done that yet, you can approach questions if you just follow these steps, and if you just solve few questions related to this thing. All right. Okay, the next type of question is valence bond theory based questions. In this case, like in this type of questions, it will be given like you will be given with a particular wave function. Let's say a psi is a wave function given to you in the form of C1 phi 1 plus C2 phi 2, and where phi 1 and phi 2 will be given as the eigen functions with eigenvalues E1 and E2. Okay, so E1 and E2 are the eigenvalues of phi 1 and phi 2 respectively. Now it might be asked that what is the probability that the system will be observed in E1, okay, or it will be observed in phi 1. So the answer will be C1 square. The coefficient of that square of that is going to give you the probability that the system will lie in that particular molecular orbital. So the square of the coefficient is going to tell you that it's going to give you the probability that the system will lie in that particular wave function. Okay, so C1 square is going to give you the probability that the system will lie in phi 1, C2 square will give you the probability that it will lie in phi 2. Okay, so this is one type of question. The other type of question based upon your valence bond theory is when the wave function is given to you and normalization condition is asked. So for normalization condition, you have to just do C1 square plus C2 square is equals to 1. So this is the normalization condition. Or they might ask that what is the percentage overlap between phi 1 and phi 2. So for that you have to satisfy this equation, that is C1 square plus C2 square plus C1 C2s is equals to 1. Here you will be given with C1 and C2, there will be some numerical values in the question. You have to put their values, calculate the value of s, where s will be your overlap integral, and that's what is going to tell you the percentage overlapping. Okay, the percentage overlapping of phi 1 and phi 2 to form psi. So this is the second type on the basis of your valence bond theory. The third type of question on the basis of valence bond theory is to find out the wave function corresponding to a given hybrid orbital. So if you have a sp3 hybrid orbital, so you will be given with the wave function in this form, that c1 phi s plus c2 phi p. Now it might also be given like this way, that psi sp3 can be given as c1 phi s like c1 psi s plus c2 psi px plus c3 psi py plus c4 psi pz. So it doesn't matter. Okay, overall their sum will be considered as a like c1 square plus c2 square plus c2 square plus c3 square plus c4 square will be considered for the p character. Okay, let's look upon this first of all, that the square of the coefficient of this phi s is going to give you the percentage s character, and the square of the coefficient of phi p is going to give you the p character. Now once you understood the s character and p character, or once you found the s character and the p character, what you have to do is you have to check whether that satisfies with the wave function or not. That means if you have sp3 hybrid orbital, so it should have 25% s percentage. So whether after doing this c1 square you are getting 25% or not, that's the first thing which you have to see. And same goes for p character as well. I will take a question to explain you this thing, okay, just to make sure that you understand this. So let's take a question to find that out. So let's talk about this particular question over here. See, the question is pretty simple. It says that one of the correct normalized sp2 hybrid orbital is, okay, you are given with the options. This question was a 4-marker question. It was asked in, I guess, in June 2017 exam. So one of the correct normalized sp2 hybrid orbital is asked. So what I told you, that first of all you have to see that in sp2 what is the percentage s character. Okay, so percentage s character will be 33.3%. And what about your percentage p character? So that is 66.67%. So that's what we got, the percentage character we have got. Now the wave function which correspond to the s orbital, these are the wave functions which correspond to the s orbitals. So the square of their coefficient should satisfy the percentage s character. So the square of the coefficient of option number 1 will be like 1 by 3 square. So that will give me 1 by 9. If I convert this into percentage, I have to multiply with 100. Will it give me 33.3? So no, absolutely not. This is going to give me 11 point something. Okay, so 11.1 something. So that's not going to be my answer. So I can just cancel out this option. Let's go for option number 2. The square of the coefficient of that is going to give me 1 by 2 square, which gives me 1 by 4. If I convert this into percentage, I get 25%. So the percentage s character which I am getting here is 25%. So again you can cancel out this option. If you check it for option number 4, again that is also incorrect. Okay, so what is left out is option number 3. Let's check it out that whether it is correct or not. So square of coefficient, so 1 by root 3 square of that should give me 1 by 3, and if when I will convert this into percentage, I will multiply with 100 and this will give me 33.3%. That's exactly correct with the s character, okay, which is matching with the s character. Now let's verify the p character as well. So for the coefficient of p, I have root 2 by root 3, and if I square this up, I will get 2 by 3, and if I convert this into percentage, I will multiply with 100. If you do that, you will get 66.67%, which is exactly with the p character as well. So this is the wave function which satisfies for the sp2 hybrid orbital, because it has correct s character and it has correct p character as well. So this is how you have to do the Huckel molecular, or use the Huckel molecular orbital theory to solve questions. Okay, Now let's take the next type of questions. The another type of question which I find very simple, and many people might not agree with it, but yeah, it's pretty simple to solve these types of question, is to find out n, l and m values for the hydrogen atom wave function, principal quantum number, azimuthal quantum number and ml values for the given hydrogen atom wave function. So there are just few points, or there are just few steps which you need to know. The first point, the first thing which you have to focus on is you have to search for, like, see the wave function. The wave function is part of three things, okay. There is a function which is like, it's three functions, okay. It's a function of r, then it's a function of your theta, okay. It's also function of theta, and it's also function of phi. So the wave function consists of three parts actually. It has radial part, it has angular part, and it has phi part. So there are three different parts which you will see in the wave function itself. So it is consisting of all the three of them, and all together it will help you to find out those things, okay, to find out n, l and m values. So what you have to search for is, you have to search for this value, e to the power minus zr upon n a naught. Remember this, okay. So in the whole wave function you have to try to search this part. Whatever is the coefficient of a naught, that is going to be the value of n, okay. So n will be what? N is going to be, or the principal quantum number will be the coefficient of a naught in the like exponential power value, okay. And remember that that exponential has to be the radial function, like that has to contain minus zr upon this. Sometimes it might happen that this zr upon a naught is also mentioned as rho, okay. So you might get it in this way, that e to the power minus rho by n. So here again you will directly get n by the denominator of rho. So you have to look for these two things, okay. If it is a function of r, then the coefficient of a naught. If it is given in the terms of rho, then the denominator of that, okay. I'll give you examples, then you will get to know. For L, you have to see, for the second thing which you have to see is minimum power of R, okay. That is going to be equal to the value of L. So value of L will be the minimum power of R. And the third thing is, you have to look for e to the power plus minus ml phi, okay. So whatever the coefficient of phi part will be there in e to the power is going to give you the value of ml, okay. It's going to give you the value of ml. So overall, if you see the question, you will be able to understand what I am telling. So here there are many wave functions which I have given, okay. Now you can easily see over here that these are the functions of rho, okay. So first of all, if you see in the first one, do you have e to the power, like we will be having it in this way, e to the power rho by n, okay, minus rho by n. So here you have e to the power minus rho. So you can write down e to the power minus rho by, you can write down it like this, e to the power minus rho by 1, right. So what is the value of n for this? So n become 1. So you got your value of n here. What is the value of L? So do you have any r, the coefficient of r over here? So no, you are not having. Do you have rho over here? Because eventually the rho depends upon r. So either an individual r or rho, that's what you have to find. So did you have this? No, you don't have that. So that means the minimum power of that is 0. So the value of L is 0. And did you get any phi part in this particular wave function? Is there any phi part? So no, there is no phi part as well. So my ml is also 0. So that's why the wave function is 1 0 0. You can check it for any other. Let's say we are looking for this. So the function over here is like e to the power minus rho by 2. So this is going to give you the value of n. So you got n is equals to 2 in this case. Now once you got n, you can check it for the others option as well. So do you have any minimum power of r? No, r is not there. So rho, so yes, the minimum value of rho, power of rho is 1. So that's why your L is 1 here. And is there any phi part? So there is no phi part. There is theta part, there is no phi part. So that's why your ml will be 0. So that's why it is 2 1 0. You can check it for anyone. Let's look upon for this. So here the coefficient of e is like e to the power minus rho by 3. So now my n value became 3 here. So I got n is equals to 3 for this. What about L? So see, the value or the power of rho is 2 here. So L will be 2, okay. And what about the ml value? So that's from the phi part. So here is the phi part. The coefficient of that is plus minus 1. So that's why your ml is plus minus 1. So that's what you got for this wave function. You can check it out for any of the wave function, and this is how it is done, okay. It's pretty simple, it's pretty straightforward. You don't have to do anything in this case, okay. One thing which you have to focus on is this all wave function are in the terms of rho. You have to solve those questions as well which are in the terms of r, okay. So try solving those as well. Okay, now before ending this video, I would give you some tips, okay. some points which might help you to solve questions from your quantum chemistry. The first tip is that if the perturbed part has odd power, remember what I am saying, okay? If the perturbed part has odd power and it is asked to find out the first order energy correction for particle in simple harmonic oscillator. So two things are very important. Simple harmonic oscillator as the system and the power of the perturbed part should be odd. So if two things are satisfied, then the energy or the first order energy correction is 0 in that case, okay? The first order energy correction for that system becomes 0. Now there are some shortcut tricks for solving commutations like x px to the power n. If you have to solve that, its answer will be I h cross n px to the power n minus 1. Whereas if you have the commutation of px and x to the power n, it will be like minus I h cross n x to the power n minus 1. So for example, if you are given to solve this x px, try to tell me the answer for that. So the answer will like this. So I h cross, and it will be like n value is 1, right, because the power is 1, so n is 1, and px to the power 1 minus 1 will be 0. So my answer will be I h cross only. So that is going to be the answer. So pretty simply you can calculate the commutation of your linear momentum operator and the position operator, okay? So that's how it will be done. Okay, let's look upon some more important points. These are certain points which I would cover in a separate video where I would discuss all the important things which you need to know, or a quick revision kind of thing for your quantum chemistry. For that it will take some time. I have to prepare notes and I have to make all these things. I have to collaborate everything at a particular point, but yeah, for now you can just see these are the commutation formula for the different angular momentum operators, okay? So Lx Ly is going to give you IH cross Lz, Ly Lz is going to give you IH cross Lx, and Lz Lx is going to give you IH cross Ly. Remember, the cycle goes like this: x to y and then y to z, okay? So if you are going from x to y, z is remaining, so z comes here, y to z, so x is remaining, x comes here, okay? So if you are going along with the cycle, that's fine. If you are going in the reverse direction, that is from y to x, that is in this direction, then the minus sign will come, okay? So this is how this has to be done. So these were certain simple types of questions which I thought that it is important to tell you, it is important to inform you regarding that, so that you don't miss out quantum chemistry completely, okay? Don't leave quantum chemistry completely. At least do these questions so that it will help you in your exam, okay? You can at least solve, or you can at least approach these questions. Well, that's it from my side, guys. Thank you so much for watching this video. I hope whatever I have taught, whatever I have explained you was helpful to you. You guys understood it well. If you have any doubt, if you have any suggestion, you can drop down in the comment sections below. Thank you so much for watching. If you liked the video, please give it a like. Do share it with your friends. Subscribe to the channel if you haven't done already. And I'll be back with new video with new content very soon on this particular channel. So thank you so much for watching. Thank you so much for giving all your love and support. I'll see you guys in the next video. Till then, have a great day. Bye bye.